Deep within the infrastructure of every major technology company lies an invisible compounding liability that never appears on a traditional balance sheet. It is a silent friction that slows innovation to a crawl, turning agile startups into sluggish monoliths and forcing brilliant minds into a state of perpetual triage. This is not a failure of market fit or a lack of visionary leadership. It is the crushing weight of technical debt, a structural decay that threatens to collapse the very digital foundations our modern economy relies upon. Technical debt is the implied cost of additional rework caused by choosing an easy, immediate solution today instead of a better, more robust approach. When a development team rushes to meet a quarterly deadline, they borrow against the future. They hard-code variables, bypass architecture guidelines, and weave complex dependencies that work in the moment but become brittle over time. Like any high-interest loan, the principal remains, but the interest payments eventually bankrupt the team's development velocity. The scale of this problem is staggering. Across the industry, software engineers spend up to 40% of their time maintaining legacy code rather than building new features. That is nearly half of the most expensive and highly leveraged intellectual capital in the world, squandered on digital janitorial work. Highly compensated professionals find themselves endlessly untangling spaghetti logic, patching deprecated libraries, and deciphering the undocumented decisions of developers who left the company years ago. Historically, the only escape from this compounding trap has been the dreaded system rewrite. These are massive, multi-year initiatives that freeze all new feature development, frustrate stakeholders, and carry a notoriously high failure rate. Attempting to manually rebuild an airplane while it is flying at 30,000 feet is a recipe for disaster. Yet companies attempt it daily because the alternative of drowning in unmaintainable software maintenance is simply unacceptable. The intelligence revolution is fundamentally altering this equation through the integration of autonomous AI agents. This is a radical departure from the simple code completion tools that merely predicted the next line of syntax in an editor. We are witnessing the deployment of sophisticated systems capable of executing complex, multi-step operations across vast and intricate digital architectures. These agents are not just typing faster, they are comprehending the structural integrity of the entire application. Unlike a localized autocomplete function, autonomous AI agents possess the capacity to scan entire repositories, mapping thousands of interconnected files and microservices. They build a comprehensive understanding of the broader architectural context, identifying how a single variable change in a back-end database might cascade through an application programming interface and crash a front-end user interface. They see the entire forest, navigating the latent space of the codebase with a precision that human memory simply cannot match. In practice, these agents act as tireless architectural auditors. They crawl through millions of lines of legacy code, proactively identifying anti-patterns, security vulnerabilities, and duplicated logic that human reviewers inevitably miss. When an outdated authentication protocol is buried within a forgotten module, the agent flags it not just as an error, but as a structural weakness requiring immediate remediation. The true breakthrough lies in the execution phase. Identifying a problem is only half the battle. Fixing technical debt requires writing the solution. These agents proactively suggest and execute massive code refactoring tasks. They isolate the problematic logic, execute rewrites to align with modern standards, and open a pull request complete with detailed context, updated documentation, and a full suite of generated unit tests, all waiting for a human engineer's final approval. This represents a profound paradigm shift in engineering workflows. The AI assumes the role of a hyper-vigilant junior developer focused entirely on structural integrity and maintenance, freeing senior engineers to focus on system design and algorithmic innovation. The human moves from being a writer of mundane syntax to a director of autonomous systems, reviewing logic and orchestrating high-level architectural strategy. The measurable impact on system stability is immediate and striking. By continuously standardizing legacy code and systematically updating deprecated dependencies, the surface area for unexpected failures shrinks dramatically. There is a significant decrease in bug propagation because the underlying foundation is constantly being reinforced. The software becomes resilient, capable of absorbing new features without fracturing under the added weight. This newfound stability translates directly into a faster deployment frequency. Engineering teams no longer have to spend weeks untangling fragile systems before launching a simple feature update. The continuous integration pipeline flows without the friction of unpredictable regressions. What used to require a careful, month-long rollout can now be deployed in an afternoon, fundamentally accelerating the feedback loop between product teams and end users. The economic implications of reclaiming that lost 40% of engineering time are monumental. When a company suddenly unlocks nearly half of its development capacity, the velocity of innovation compounds. Teams can experiment faster, iterate on user feedback instantly, and tackle ambitious roadmap items that were previously shelved due to resource constraints. The financial liability of technical debt is converted back into an asset of pure momentum. Beyond the balance sheet, the psychological impact on the engineering culture is transformative. Maintaining outdated, poorly written legacy code is notoriously demoralizing, often leading to high burnout and turnover rates among top talent. By offloading the drudgery of software maintenance to autonomous agents, the daily experience of the developer returns to its creative roots. The dread of archaeological excavation is replaced by the thrill of actual engineering. Yet, integrating autonomous systems into core infrastructure is not without profound risk. Trusting an AI to rewrite the foundational logic of a financial transaction system or a healthcare database requires an immense burden of proof. If an agent hallucinates a variable or misunderstands a critical business rule during a refactor, it could introduce catastrophic vulnerabilities that slip past human reviewers lulled into a false sense of security. To mitigate the systemic risk, the industry is adopting rigorous containment strategies. Agents are deployed within strictly sandboxed environments, isolated from production data. They do not have the authority to merge their own rewrites. Instead, their output is subjected to aggressive continuous integration pipelines, where automated testing suites verify every logical pathway before a human engineer ever sees the proposed changes. The architecture of these solutions is evolving into sophisticated multi-agent systems. In these setups, one agent is tasked with writing the refactoring logic. A second independent agent acts as a security auditor to aggressively attack the new code, and a third agent generates edge case tests to validate performance. This adversarial approach ensures that the output is mathematically and logically sound before it ever touches the primary repository. As these systems mature, the traditional excuse that a product is delayed due to legacy constraints will become unacceptable in the marketplace. Companies that successfully adopt AI-driven refactoring will iterate at a pace their competitors simply cannot match. Technical debt is transforming from a permanent, unavoidable tax on software development into a solvable equation, creating a massive competitive divide between those who automate their maintenance and those who do not. We are already witnessing case studies where massive, monolithic applications are being broken down into agile microservices over a matter of weeks. Tasks that once required armies of highly paid consultants and years of perilous migration are being orchestrated by AI agents working around the clock. They dissect the monolith, untangle the dependencies, and generate the new service boundaries with a surgical precision that human teams struggle to achieve. This shift demands a radical evolution in the skill set of the software engineer. The premium is no longer on the ability to memorize syntax or manually track variables across hundreds of files. The future belongs to those who excel at prompt engineering for complex systems, those who can clearly define architectural boundaries, and those who possess the critical thinking required to evaluate the logic of a machine. We are entering an era of unprecedented leverage, where the democratization of maintenance allows incredibly small teams to manage massive global code bases. A single developer, armed with a swarm of autonomous agents, can now wield the operational capacity of an entire legacy IT department. The constraints of human bandwidth are being decoupled from the scale of the software they can create and maintain. The broader economic shift is just beginning to materialize. Billions of dollars currently trapped in the endless cycle of maintaining outdated, fragile systems will be liberated. This capital and human ingenuity will be aggressively reallocated toward frontier technologies, complex problem-solving, and user-facing innovation. The anchor is being lifted, and the entire technology sector is preparing to accelerate. Ultimately, fixing technical debt through artificial intelligence is not merely a housekeeping task or a marginal optimization of the workflow. It is the necessary unlocking of the next era of human progress. By securing the digital foundations of our infrastructure and delegating the burden of the past to autonomous systems, we are finally free to build the architecture of the future.